All right, algae, Klein, Ellis, Evans right here, Ferg is here, Gooden, Harris, Jackson's right there, Johnson, McClin, McElroy, Robinson, okay, Stackens, Summers, Townsend, Valentine's here, Washington, Whitley's here, and Sierra Williams, and Tyrus Williams. All right. All right. Now we're going to cover arguments with quantified statements. All right. So arguments with quantified statements. If a property is true of everything in a set, then it is true for any particular thing in the set. So all men are mortal. Socrates is a man. Therefore, Socrates is mortal. So, for all men, all people, people are mortal. Socrates is an element of people. Therefore, Socrates is mortal. Let's see here. Simplify the k plus 1 times R. Simplify that. We know that x to the m times x to the n equals x to the m plus n, right? Simple college algebra. And we know x to the 1 equals x. So, you can simplify this as being r to the k plus 1 times r to the first. So it'd be r to the k plus 1 plus 1, or r to the k plus 2. Sound about right? This is true for all m and n. And x to the first is x. So this is like x to the first. And then, because this is true for all m and n, we add 1 to the k plus 1 and get k plus 2. R to the k plus 2. Universal modus ponens. Universal modus ponens. Formal version. For all x, p of x implies q of x. P of x for a particular x and therefore q of x. Looks like modus ponens, but informally it's like if x makes p of x true, then it makes q of x true. A makes, oh, this is not x, this is supposed to be A. And that's supposed to be A. Sorry about that. If x makes p of x true, then x makes q of x true. A makes p of x true. Therefore, A makes q of x true. So, for all x, p of x, if p of x, then q of x. P of x is true for a particular A. Therefore, q of A is true. Yeah. Using quantifiers, variables, and predicate symbols, rewrite the following statement. If an integer is even, then its square is even. K is a particular integer that is even. Therefore, K squared is even. So, let's say, let's look at this. If let's see here, for all little z element of even, if z is an element of even, then z squared is element of even. K is an element of even. Therefore, K squared is an element of even. You see how that's modus ponens? Yeah. Let's see here. If T is any right triangle with a hypotenuse C and legs A and B, then C squared equals A squared plus B squared. A triangle is a right triangle with both legs equal to C and hypotenuse C. Therefore, C equals the square root of 2. So, all right. Something a little bit different. For all integers x, for all x element of integers, if x is an element of even, if and only if there exists a k element of integers such that x equals 2k. Uh, So that, given that is true, prove that if two even integers m and n are added together, the result is an even number. So, M equals, there is an element of even. And from this, therefore, M equals 2S, for example. Uh, where S is an element of integers. N equals is an element of even. Therefore, N equals 2T, T being an element of integers. Then you can say M plus M equals plus N equals 2T plus 2S, which is equal to 2 times T and S. And we know that T and S are integers, so their sum is an integer. So say U, and U is a element of Z. Therefore, and so by therefore, M and N plus N is an element of even. See how that worked? Kinda, sorta? Kinda? I have a little bit more detail in my notes here. So M is a particular integer, therefore M equals twice some integer R, or S. Same logic for N. If a quantity is an integer, then it is a real number. S and T are integers, therefore R and S are real numbers. For all A and B and C, if A, B, and C are real numbers, then A, B plus AC equals A times B plus C. 2R and S are particular real numbers, therefore 2R plus 2S and 2 plus 2T equals 2S, 2 times S plus T. For all U and V, if U and V are integers, then U plus V is an integer. S and T are two particular integers, therefore S and T are integers. Therefore, the S plus T is an integer. If a number equals twice some integer, then that number is even. 2 times s plus t equals twice the integer s plus t. Therefore, 2 times s plus t is even. If r plus s, or s plus t is even, then m plus n is even. By modus ponens, 2s plus t is even, therefore m plus n is even. It's a 2-page argument and proof, but this is the extent of it, the basics of it. Let's see here. Universal modus tollens. In formal terms, for all x, if p of x, then q of x not q of a for a particular a, therefore not p of a. You can see where the modus tollens comes in. Just has a universal quantifier at the beginning. If x makes p of x true, then x makes q of x true. A does not make q of x true, therefore A does not make p of x true. So, all human beings are mortal. Zeus is not mortal. Therefore, Zeus is not human. So, what is the conclusion of the following argument? All professors are absent-minded. Tom Hutchins is not absent-minded, therefore what? He's not a professor. All right, proving the validity of arguments with quantified statements. Let's see here. Definition. To say that an argument form is valid, the following means the following. No matter what particular predicates are substituted for the predicate symbols in its premises, if the resulting premise statements are all true, then the conclusion is also true. An argument is called valid if and only if its form is valid. It is called sound if and only if its form is valid and its premises are true. So, using diagrams to test for validity. All right. All integers are rational numbers. So you can see that if a property is true for rational numbers, it is true for integers, because all integers are rational numbers, as shown by this little diagram. Now, revisit this one. All humans are mortals. That's the major premise. And that was the, I can't spell. All humans are mortals. This is not mortal. Therefore, you can see quite plainly that he can't be human, because he's not mortal. Now, using this, all humans are mortal. Felix is mortal. Therefore, Felix is a human being. Is that a valid argument or not? All human beings are mortal. Felix is mortal. Therefore, Felix is a human being. Well, what if Felix was right here? Yeah, Felix.
Does this say that mortals are also human beings?
Huh?
Does it say that mortals are also human beings?
Humans are mortal. Felix could be a cat. Cats are mortal, but they're not human beings. So you can show here that Felix could be immortal without being within the human sphere. So therefore, it is a invalid argument. Converse error. That would be what the Felix argument is. It's converse error for all of x. If x makes p of x true, then x makes q of x true. A makes q of x true, therefore a makes p of x true. That's an invalid conclusion. Inverse error is the contrapositive of that. If x makes p of x true, then x makes p of x or q of x true. A does not make p of x true, therefore a does not make q of x true. So that's like saying all humans are mortal. Felix is not human, therefore Felix is not mortal. That's not a valid conclusion. It is an invalid conclusion. Let's see here. Use diagrams to test the following argument for validity. Let's see here. No polynomial functions have horizontal asymptotes. This function has a horizontal asymptote. Therefore, this function is not a polynomial function. So, you have two circles here, polynomials. Polynomial functions. And then you'd have functions with horizontal asymptotes. This function has a horizontal asymptote. Therefore, this function is not a polynomial function because it can't be in this circle if it's in this circle. So, yeah, using diagrams to test your validity. Seeing it in a visual form. Creating additional forms of argument. Informal, universal transitivity. Let's see here, they're using PQ and R. For all of x, P of x, then Q of x. For all x, Q of x implies R of x. Therefore, for all x, P of x implies R of x. Just the transitivity property that we saw earlier, just with the universal quantifier. Okay. Little remark on converse and inverse errors. One reason why so many people make converse and inverse errors is that the forms of the resulting arguments would be valid if the major premise were a biconditional rather than a simple conditional. Consider, all the town criminals frequent the den of iniquity bar. John frequents the den of iniquity bar. Therefore, John is one of the town criminals. That is converse error. A variation of converse error is useful provided it is used with caution. For every x, if P of x, then Q of x. Q of A is true for a particular A. Then check out P of A because it just might be true. This is used by doctors and auto mechanics to diagnose problems. So, if you have a fever and a cough, if you have the flu, you have a fever and a cough, right? You have a fever and a cough. So check for the flu. Don't jump to the conclusion that it's the flu, but rather check it out as a possibility. So it can be useful. Converse error can be useful, but it is not a valid form of argument, and it cannot count on the results. Well, that basically wraps up chapter 3. There will be a test on chapter 3 or quiz on chapter 3 on Thursday. The question is we have 40 minutes left. Do you want to jump into chapter 4, or do you want to easy day today? Easy day? Okay. We'll call it a day here then, and we'll reconvene on Thursday for the test. Have a good day.